Hello and welcome to the Research Matters podcast. I am your host Aarti Halbe, and today we have with us Professor Bedangadas Mohanty, the Infosys Prize winner for Physics for the year 2021. Professor Mohanty is a professor at the School of Physical Sciences, National Institute of Science, Education and Research, Bhubaneswar. He has agreed to unfold before us the exciting world of experimental high energy physics that involves temperature of trillion degrees Celsius and particles trillionth of a meter banging into each other. Welcome, Professor Mohanty. We are so glad to have you here with us.
Thank you very much.
The Infosys Prize is a prestigious prize, India's very own prize in the field of research. Professor Mohanty has been awarded the prize in physics for his investigations of the nuclear force. Professor Mohanty, what was your first reaction when you came to know that you have been chosen for the prize?
My first reaction, I was very happy to get this recognition, being part of a very illustrious list of past laureates and selected by a jury whose work I immensely respect. They are peers in the field. So it was very satisfying to get this recognition from peers, thanks to the Infosys Science Foundation.
Professor Mohanty works in the area of experimental high energy physics. This branch deals with understanding the interaction between the elementary particles that make up the universe. By particles, you may think of dust particles, or atoms, or molecules. But the particles we are talking about here are tinier than the tiniest. We are speaking about the particles that make up the proton, which make up the nucleus of the atom, which is the fundamental particle that defines an element. So, what exactly keeps the nucleus together?
Suppose we are going to build a house, then we need some building blocks, which are bricks, and something to glue together, which is the cement. Similarly, if we want to build our universe, which is a very daunting task, most part of the visible universe, what one would require is the building blocks and some forces which hold them together. Whatever you see around is made up of electrons, quarks, and gluons. They are the building blocks of this visible universe. Now, what holds them together? There are four kinds of interactions which hold them together. One is strong force or the nuclear force, electromagnetic interaction, gravitational interaction, which is responsible for us walking, moon moving around Earth, and weak interaction. Now, electrons are freely available. Flow of electron is the current. But these quarks and gluons are not freely available. They were available when our universe was a microsecond old. That means 10 to the power minus 6 seconds. Now, we need these quarks and gluons to bound them to form protons and neutrons. Then the protons and neutrons have to be bound together to form nucleus, and then you form the atom. This force is the strong force, which binds these things together. If this force wouldn't have existed, life won't exist.
Experimentalists in this field are not very common in India. What got you excited about this field and what led you to follow this?
Most of our facilities are abroad because of the complexities and the funds required to build them. But what really excited me is we get a chance to address some of the profound questions in science. For example, how did we get mass? What are we made up of? And those basic blocks, what are their properties? How this force which binds together things work? A chance to work with best of the minds internationally is what excited me to start with. Course of it, I realized It also makes you humble. See, Earth is a planet in a solar system. There are many planets. Our solar system is one among the millions of such systems in our galaxy, which we call Milky Way. And we are not at the center of the galaxy also. We are at some corner. And there are millions and billions of such galaxies. So doing this science also is a very humbling experience. One other thing we learned, you need a diverse expertise to build these experiments. So we learn to share. We learn to collaborate and respect others' opinion. We learn to convince people that our idea will work. In our publication, there are thousands of authors. Everybody has to agree with my idea to get it published. We learn to be patient with so many people, with a lot of excitement and smart people. You have to be patient. And we also learn that one is not indispensable, because the collaboration to move its project will find someone else. And lastly, which really I sort of excited me, is to get to know different cultures and sharing our culture with the community.
Professor Mohanty, you study particles, their collision, forces between them, and how they interact. How does studying all this help us?
Important aspect is we understand how this universe got formed, how it evolved to the current stage from basic science perspective. Now, when we are doing these experiments, we need sophisticated techniques, technologies, detectors. Those have found application for societal benefits. For example, the detectors that we use for detection are used for medical imaging application. They can replace the ordinary X-ray with a more three-dimensional image of the things with high resolution. Another thing is we require accelerators, machines which will accelerate particle to high energy. Those accelerators can be used in turn, the technology, to treat cancer by proton therapy or ion therapy. There are much advantages compared to normal way of treating. Lastly, the amount of data that we get, the techniques that we use led to concepts like World Wide Web or grid computing. So it's very satisfying to address a basic science problem, and also very satisfying to see that what we develop can be also used for benefits of society.
One of your significant contributions is towards the establishment of phase diagrams of quantum chromodynamics. Can you explain in simple layman terms what this means?
Any physical system or matter, when you subject it to external parameter like temperature or pressure, it will undergo change. The matter organizes itself in a different way when it is subjected to heat or pressure. For example, which all of us know, is water. Water is in liquid state. Its another form is ice, which is solid state. And the third phase is vapor, which is in gaseous state. How do you get to that? By applying temperature and pressures, you can go from one phase to another. This how water changes with temperature pressure is very widely studied in science and precisely known. So you can find it in textbooks. It is NCERT textbooks, everywhere you find this. Now, there are, as I mentioned in the beginning, there are 4 interactions. And strong force, electromagnetic force, gravitational force, and weak force. Water molecules interact through electromagnetic force. and we have these phases of water, liquid, gas, and solid. What I am set out to do is, if the matter is interacting through strong force, what happens? Does it also have a liquid phase, a gas phase? Is it similar to that of water? So that is the experimental program. The matter which all of us are made up of, how many phases it has when you change temperature and you change pressure. Our current understanding is there are two distinct phases. If you hit matter to trillion degrees Celsius,
Okay.
a million times hotter than sun, which we achieved in the laboratory,
Oh, wow.
then you find that it is like a liquid and it flows much more smoothly than water. If you go down in temperature, it is in a gaseous state.
Okay.
Okay. Now we are trying to figure out this liquid to gas, the way it goes from liquid to gas, is it same as water goes to vapor, or it is different? So that is what we are trying to figure out. One more thing I will add here. When we heated matter to a trillion degrees Celsius, million times hotter than sun, core of sun, the matter melted into its fundamental building blocks, quarks and gluons. Now, I'll come back to this water. Water is made up of hydrogen and oxygen. Hydrogen burns. It is used as fuels to sending rockets and things like that. Oxygen supports burning, but water extinguishes fire. Suppose I give you water, then it is very difficult for one to find out properties of hydrogen and oxygen. See the example, hydrogen burns, oxygen supports burning, but if I give somebody water and ask him or her that, can you tell what is the property of hydrogen and oxygen? Very difficult, because water extinguishes fire. Similarly, the property of what all of us are made up of, how will you know? You need to create that matter in the laboratory. So we created this matter in free state, and now we are studying its property. So it behaves as a liquid which flows much more smoothly than water. We're trying to measure its conductivity. So this is the excitement to find out more about what we are made up of. That's related to this phase diagram of QCD.
I have one very basic doubt. So you mentioned that you achieved a temperature of trillion
degrees Celsius.
How did you achieve that temperature?
Very good question. So what we do is we collide two ions, heavy ions, like gold ions. Ions means they are stripped of all its electrons. Very high energy. When you collide, then a huge energy density is created. Energy per unit volume is large. Then there is a basic law in physics called Stephen-Boltzmann law, tells that if you pump in large energy in a small volume, then you could go to very high temperatures. So that is how we reached. But the collisions, the matter stayed only for a 10 to the power 10 to the power 10 times of a second.
Okay, that's okay.
As a result, it did not affect any surrounding. For a momentarily, temperature went up. And the challenge is, within that moment, we have to try to make measurements and understand and interpret what I was telling you.
An interesting fact to note is that Professor Bidangadas Mohanty works in India in spite of getting an offer to work in one of the most prestigious institutions. In your CV, you have mentioned that you have declined an offer from the Lawrence Berkeley National Laboratory. Can you share why you declined it?
Yeah. So Lawrence Berkeley National Laboratory is a beautiful place to work. I was a postdoctoral fellow there. It's also the laboratory where my field was born. And I distinctly remember the day I reached the laboratory to join. That's the day the laboratory Professor George Smoot got the Nobel Prize. The same day I reached, and there was big function. Now, towards the end of the tenure, after a very rigorous selection process, they offered me this position. But I always wanted to come back to India. I very humbly turned down the offer so that I can work in India, spread this excitement of doing this science in my field, or one day perhaps set up a small scale experiments within this country. Like we go to other labs to work, it is a dream to see if other people can also come in and work in our place. So I very humbly turned it down, but they kept the fundings going even after that. And it remains like my second home.
We understand that you are actively involved in the STAR experiment. Can you elaborate something on how you staying here in India can contribute to the STAR experiment?
Okay. I will take little bit time on this because you are asking me my prime 20 years of the research. So I will take little
Definitely
minute or two more. The STAR stands for Solenoidal Tracker at RIC. RIC is the Relativistic Heavy Ion Collider. It's an abbreviation of an experiment called Solenoidal Tracker at RIC. It is situated in Brookhaven National Laboratory in near New York in USA. It is a collaboration of 72 institutions from 15 countries and close to 700 people, scientists. And these scientists have been running this experiment, build and run this experiment for last 21 years. Experiment is so complex that we need diverse kinds of people with diverse expertise. And that's how this is a big collaboration. What it does is it collides this gold ion, which I was mentioning, at high energy. Now, the goal was or is to create this new state of matter, free state of quark and gluons, which all of us are made up of, and understand its properties. And I mentioned about some of the properties earlier in the discussion. Now, when I was doing PhD around 1999 and 2000, I was asked by the Indian group to go there and do some feasibility studies on simulations to put an Indian detector there. So I went there, and prior to that, I tested a prototype of the detector using CERN facility, and it worked well. So my simulation was successful, and an expert team allowed us to install an Indian detector in that experiment. So the Indian team at that time consisted of 6 institutes. What we built is called as a photon multiplicity detector. Photons are light particles. We built 85,000 small unit detectors, put it together. The building, the designing, installation, commissioning was entirely done by us. Took the detector, installed in that experiment to capture photons. And we took the first data. Then I worked with a PhD student, now a scientist in BRC, Dr. Pawan Kumar Netrakanti. And it was such a joyous occasion to see that all these 85,000 small detectors cohesively working and in an international setup and giving the data. I cannot express it in words how that feeling was. Due to my contribution, I was asked to present the first results to the international community. And the paper got published in one of the topmost journals in physics called Physical Review Letters. Now, this was work entirely done by Indian team, mostly from India. What we used to do is go there, collect data, maintain and operate our detector. Now, with this experience, many more colleagues from India started working on the data. So I thought, let me branch out to other systems in the experiment. In the heart of the experiment is a detector called time projection chamber, which was built by the Berkeley group. But it had a limitation. It is not able to identify particles at high speed. So the collaboration said, can you devise some technique where we can start identifying particles at high speed? It will increase the science and physics capability of the experiment. So I teamed up with a colleague, Dr. Zhangbu Zhu, who is a senior scientist at the Brookhaven National Laboratory, and gave that technique. The technique was published in a prestigious journal, Physics Letters, and now has more than 300 citations. In the meantime, I made it a habit to read each and every publication coming from the experiment. And it was very appreciated in the collaboration. Because of this experience, the then head of the experiment, Dr. Timothy Holman, who is currently Associate Director of Office of Science of Nuclear Physics in Department of Energy, Government of USA, appointed me as a leader of a physics working group. There are 6 working groups in the experiment, led by 6 physicists. I became the leader of one of them. Now, there also I contributed quite a bit. As a result, the next head of the experiment, Professor Nu Shu from Berkeley, appointed me as the physics coordinator of the experiment. Now, this first time an Indian took up this position in such a multi-institute, multi-country experiment. Now, what's the role of it? The physics coordinator actually goes, unless the physics coordinator approves, the papers do not go for publication. Physics coordinator drives the science direction of the experiment. Now, in the 3-year period where I was physics coordinator, the experiment published 50 papers, 11 of them in the top journal Physical Review Letters. And we discovered the 2 heaviest antimatter nuclei till date in the laboratory. Those were published in Nature and Science. Then about 50 students got their PhD during my tenure. And our experiment collaboration gave 400 talks at international forum. I used to work 18 hours a day, and mostly overnight, because that's the daytime. Dominantly, the collaboration was dominantly from US groups. So that was the effort. It was such a highly successful thing that I was then next level. I was moved up to the deputy spokesperson of the experiment. This is the second highest position in the experiment. Again, first Indian to head this position in an international running experiment. That time, I co-founded this program to study the phase diagram of QCT, and also gave a 10 years of path forward. Now, all these also brought me recognition from the US community. I was given the chance to present at the highest conference in our field, the Quark Matter. And also the US community elected me as a fellow of American Physical Society. A very rare honor for a person outside US getting this thing. So in summary, along with my collaborators, what I did in this star experiment, measured photons using an Indian detector, found new technique to improve the best detector in the experiment, discovered the heaviest antimatter nuclei, measured properties of what all of us are made up of, the quark gluon plasma, and set up a new direction through a program called beam energy scan, which is now trying to lay out the phase diagram of strong interactions.
Coming to India now, how does the future look like for experimental high energy physics in India?
I think with our resources and with the current expertise which we have built up by participating in international programs, two things which we can really focus on is building a good underground laboratory to do physics related to neutrinos, physics related to dark matter, or searching fractionally charged particles. This can be done. Second is one can also use our research reactors, nuclear reactors, which generate power. While they are generating power, clean energy, they are also producing neutrinos. And these neutrinos has immense value if we can measure and can do very exciting physics like sterile neutrino search, coherent scattering, elastic scattering of neutrino with nucleus. So these are clean two areas where we can set up high energy experiments in India.
So you're saying that these can be set up right now without any extra infrastructure investment, sort of. I mean, at least the nuclear reactor part.
Yes, it is possible, but one has to, of course, invest in building detectors to make this. But I think we can pull together the existing resources, and it is feasible to do such experiments.
India has plans to establish the Indian Neutrino Observatory. How can establishing it help the research in particle physics?
Yeah, thank you for this question. Neutrinos are such a particle which is found everywhere. I mean, it is found from Earth, from atmosphere, from star, from reactor, from accelerator. And the most important thing is very difficult and challenging to study it, both theory and experiment. Now, experiments have shown that the neutrinos have mass.
Okay.
Now, but this absolute mass scale is not known. What exactly are their masses is not known. And it is a big, fundamental, open question that what is the absolute scale or mass scale of neutrino? INO, through its unique ICAL detector, has ability to differentiate between neutrinos and antineutrinos. Hence, it is one of those rare experiments worldwide which can address this fundamental question of absolute mass scale of neutrino. So that is why it's very important. But if we delay it, then there are competitions and it may go. Now, what we can do is, there are two things. One direction is setting up world-class facility within India. So we need underground laboratory. There are other possibilities also, like in Jadugada Science Laboratory in Jadugada, one can set up. There are other places to do experiments which INO is doing, as well as I mentioned, searching for dark matter or neutrinoless double beta decay. Many interesting physics can be done.
How would having a neutrino observatory in India help the research community here?
Now, a large-scale international experiment running in India will automatically develop or train human resources in experimental science. Activities such as large-scale international experiments and national and international experts coming here will expose our students to cutting-edge science as well as technology. our industry will have a chance to develop those detector technology. And within India, the related fields can be developed. Currently our young people are involved in tabletop experiments. But having such a facility will make them acquainted how to work in large scale, in a many order of magnitude large scale of experiment, how complex it is, how to collaborate, how to share, how to work together, how to challenge each other with ideas. So once these proposed high energy physics experiments start in India, the brain drain would also taper off, because highly trained and competent young people will get scope to work in their own country. So, this infrastructure, which is associated with INO and such experiments, are really needed. Another interesting thing, I'm involved in writing this mega science vision document which has been initiated from the Principal Scientific Advisor Office. And there you will find a lot of details. We have gone through what are the advantages of doing this, including benefit to other branches like material science, geology, biology, where if we build an underground laboratory, they can do experiments in radiation-free environment. So there is immense benefits of doing such experiment. But, there is some delay in INO going ahead, which is not in hands of the scientists. So it seems that the progress of INO towards final aim is getting delayed due to various regions. Now is the time for the people of this country to stand behind the scientists and support this effort. In this scenario, I'm reminded about one incident, and I want to share with you. This is by Professor Robert Wilson. He was the founding director of Fermilab, Fermi National Laboratory in US. He passed away last year. He was not only a pioneering scientist, but was a very influential spokesman for science. And I will tell one quote, and which should tell why we should have these experiments set here. He was asked by the Congressional Joint Committee on Atomic Energy 1969 by a senator about what is the value of setting up these high energy experiments in the country. So I'm now quoting. He said, "It has nothing to do directly with defending our country, except to make it worth defending."
Very true.
And I think that's all I want to convey, that we need to build such facilities which we will all be proud of.
Professor Mohanty, some people are afraid that building an underground neutrino observatory may cause harm. What would you tell them?
Yeah. Every day, thousands of neutrinos are crossing through us. And there is no danger associated. For centuries, neutrinos are passing through Earth, and we are all exposed to it. And there is no danger from neutrino. Underground laboratory, there is a science reason why we need it, because we want to stop all other backgrounds, and we want to detect this particle. Otherwise, the signal will be embedded in a huge background. Absolutely no issues, no harm in having these underground laboratories. We have routinely in mines.
Correct.
So both from neutrino perspective as well as building the laboratory perspective, there is no issue scientifically.
So just before we conclude, what message would you like to give our young viewers, readers, listeners?
Okay. I will I will actually borrow a quote from Professor C.V. Raman, which I like a lot. And whenever I address younger people, I read this quote. So if you allow me, that's the message. I completely agree with it. This is from Professor C.V. Raman. So let me read it. He was actually addressing young people as an outreach program, and he told this: youth is the most glorious time of all. I have said elsewhere that most of the great discoveries in science have been made by young people. It is not the experience or wisdom that old age brings, but the freshness of outlook, the indomitable desire to achieve, which is a characteristic of youth that makes discoveries possible. It is this that makes life worthwhile. If only you realize this and realize that here I am still young, let me see what I can do, that all discoveries will become possible. So this is the message I would like to give.
Thank you very much, Professor Mohanty. It has been a pleasure speaking with you. Thank you for listening. This podcast was brought to you by Research Matters, a SciComm initiative by Gubbi Labs. For more such science-based stories and podcasts, log on to www.researchmatters.in. Until next time, stay tuned.